Today, we will talk about the sample preparation in biochemistry. So I will give you some more information on what is key towards reliable results. I will split it up in different parts. Today, we'll treat part 1, which talks about basic reaction types, calibration, and QC. The next meeting, we go more profoundly into bilirubin or more complicated methods. But before we start, I want to give you a brief introduction why these trainings are organized. And then as well, we go through the different steps of the day. The first one will be the timing. The second one will be calibration and QC. And then there will be time for questions and answers. Okay, brief introduction on who we are. We are Cypress Diagnostics. All our products are made in Europe and we are based in Belgium. We have been founded in 1995 and we are ISO 13485 certified. We are an in vitro diagnostic specialist and actually we have 75 million tests per year that we provide to laboratories and to distributors. In order to make sure that you have everything in place and that the laboratory has everything in place to do the analysis in a correct way, we offer a platform going from analyzers to the training support. So we offer the analysis and as well the validated reagents on these analyzers. Next to that, we also introduce you calibrators and controls, and we have the consumables to do the daily, the monthly, and the yearly maintenance. Next to that, we have a trained team to give you the support on our reagents and on our instrumentation. What is a commitment that we do? 45% of our employees are fully dedicated to the quality of the products and to your satisfaction. That means that 45% is or working in quality control, or working in regulatory affairs, or working on the training and the support department. Also, in addition, we have more than 100 training courses per year, internally and externally, to retrain and to update the skills for team. That makes that all of the procedures are strictly followed every time and that we can assure you the quality lot after lot and batch after batch. To give you a brief introduction of for today, I do want to retake one of the slides that we had in the previous presentations. So here in the first quality of reagents presentation, we saw that in case the laboratory practice is not respected by the laboratory or in case wrong results come out, this has a high and a severe impact on the patient. So we want to get clear, correct, and consistent results. And today I will introduce you 2 key points that will help you to get these clear, correct, and consistent results. Before we start, just a small slide on what happens in a biochemistry reaction. We always start with light intensity. We always start with a light source. It can be a LED or it can be a halogen lamp, but the point is it is a light intensity source. And that one needs to be transmitted towards an analyte concentration. If we make sure that we do it the right way, we are also sure that we have clear, correct, and consistent results. This is the pathway of the biochemistry reaction. So as told, we start with the light source. That light passes through a filter and then passes through a cuvette or a flow cell. Then that light passes through and goes to the detector where the analog system signal is transported towards a digital signal. That means that at that time we speak on an absorbance. Then that absorbance still needs to transmit it towards a concentration. And that is actually the calculation part. If we look at all of this process, actually we can split it up into 2 points. First of all, we see that we can go from the light source or the light intensity towards a digital signal, which is the absorbance. And that is related to the timing. So the main question that we are going to ask this session is, when do we need to measure? This depends on the type of reaction that we are going to see. The second part is, if we have this right absorbance, how can we transport it towards or transmit it towards a right concentration? This is due to the calibration. And then we have to ask the key question, what to compare with? The first step will give you a correct absorbance. The second step will give you a correct factor. And if we multiply to both of them, then we will receive a correct concentration. In this presentation, we'll go step by step. I will first focus on the timing and the different types of reactions. And in a second phase, I will go through the concentration, so the calibration. All right, let's go to step 1. So we'll focus on getting a correct absorbance. What you see here is actually different type of samples and different type of colors. You see that it goes from light red to dark red. This color intensity is actually related to the concentration. The lower the coloration, the lower the concentration will be. The higher the coloration, the higher the concentration will be. So that also means that depending on the color that is formed, you will get another concentration. And actually what we see is that in biochemistry, we have 3 types of reactions. And it's important to know which type of reaction you are dealing with to measure it at the correct time, because this will determine whether you have a correct absorbance or you don't have a correct absorbance. All right, we have an endpoint method. That's the first one. We have a 2-point method or a fixed time method, and we have a kinetic method. You already see now that the curves or the profile of these reactions is completely different. And I will go into detail now one by one. Okay, let's start with the first one, the endpoint reaction. You see here the reaction profile, and I will go through it step by step to see what is happening. If we have an endpoint reaction, of course, first we're going to calculate the reagent blank or to measure it. That means this is the basic color of the reagent. As you can see, for instance, for albumin, this is lightly yellow greenish. This is the basic color of the reagent. Then when we add the sample to that reagent, we see that there is a coloration or color forming period going on. That is what we call the incubation period. You also see that the line or the curve that you see is not straight, it's not linear. So in that section, we cannot do anything or we cannot make a measurement. However, you also see that in the green part, we enter a stable period. That means that the absorbance goes up, and at the first one level, it stays at a plateau. And it is on that plateau that we are going to measure, because we know during this time frame, the reaction will not change and the absorbance will not change. You also see in the end that the curve is dropping again. That means that we have reached the end of the stability period. And there you cannot measure anymore, because then you will have false absorbances. Okay. So one single absorbance at the plateau level will give you one concentration. So what we always will see is that the concentration will be equal to this absorbance times the factor. I have added there again the tubings. So you can see that a light colored tube will give you a low absorbance. A higher colored tube will give you a higher absorbance, and that is where you see the difference between patients. All right. Some examples of these endpoint methods are glucose, total protein, albumin, triglycerides, and so on. Okay, but how can you recognize whether you are in an endpoint reaction? Well, there are 2 ways to know. First, you can look at the IFU or the manual, And there will always be a certain amount of phrases that will come back. It's always the same. That says, first, mix and incubate for a certain number of minutes at a certain temperature. Then it always says, okay, then you start to read the absorbance of the sample, and the color is stable for X amount of minutes. Or when you use the analyzers of Cypress, then the CYANVision, the CYANSmart, the CYANElite, actually you can see that the programming is fully validated on these machines. And then in the application sheet, you will find that you can prepare several samples simultaneously. That means that for an endpoint method, you can prepare everything at once because the absorbance goes to a stable period anyway. Then you need to mix and incubate at a certain amount of minutes at a certain temperature. And then, of course, after that incubation time in which we spoke that the reaction is going up, we need to aspirate and we need to measure within that time frame. To give you an example on the glucose, we see that on the IV it's written that you incubate 10 minutes at 37 degrees or 15 minutes at 15 to 25 degrees or at room temperature. And then it said color is stable for 40 minutes. That means during that time frame of 40 minutes, you can measure the sample without the absorbance being changed. If we look at the application sheets, you will see the same. So we mix and we incubate 10 minutes at 37 degrees or 15 minutes at room temperature. And then after that incubation time, we'll aspirate and measure within 40 minutes after the preparation. So when we execute this on a semi-automate, then you will see that first of all, we will prepare the sample simultaneously. Then we are going to incubate the samples outside the analyzer. That is very important. So you have a certain incubation time, but you need to do it outside the analyzer. You can do this at 37 degrees. You can do this at room temperature. There is no difference in the absorbance level that will be reached. It will always be the same, whether you measure at 37 or whether you measure at room temperature. The only difference is that the speed of coming to that stable period will be different. If you do it at 37 degrees, it will be faster than doing it at room temperature. Then, once that is done, we go to the stable zone in which you can measure. That is the 40 minutes for glucose, in which you can measure. And then, of course, after the dropping of the curve, then it's too late to measure. You cannot measure anymore after the stable zone. So let's give you a short demo and Linda will demonstrate it to you.
Okay, so what we did here, I've already prepared the sample. I put them in the tube. So we will now add the reagent to them. So we add the reagent and then we vortex shortly. So what's typical for the endpoint is that here we can do all of the samples at once. So you can see here that the color changes immediately, but that doesn't mean that the reaction has already arrived at the stable period. It will take some time until the reaction arrives there. So we can do all the samples at the same time. Then we start our timer. Sorry. And to accelerate the reaction, well, we can always do this at room temperature, but we can also put the samples in an incubator at 37 degrees to speed up the reaction a little bit. Then in this case, for today, we will not wait for the 10 minutes, but you understand the principle. You incubate for 10 minutes, and then you can take all your samples and you start the reading. That's it.
So, as we saw, it's very simple to do it. So the key point to take home with an endpoint method is that it is fast. So you can do many samples at once. If you have like 20 samples to do in the laboratory for albumin or for total protein, okay, you can just prepare all them at once. And then actually you have 6 seconds in the analyzer per sample to do the reading. Important to know is that the incubation is outside the analyzer. Also important to note is that 97% of the Cypress diagnostics methods can be measured or can be incubated at room temperature, and that you do not need an incubator. However, if you want to speed up the reaction time or the incubation time, then at that time, actually, you can just use an incubator at 37 degrees and you will get your results faster. But it's not necessary to get the right absorbances. Then in terms of easiness, well, you saw it's an easy execution. You add the sample, you just add the reagent, and then you wait until you can measure it. 71% of the Cypress diagnostics methods are endpoint methods. And then you have the calculation. Well, yeah, calculation, the coloration that being formed is equal towards the concentration, but we need a factor for it. The good news is this is automatically done by the analyzer, and I will go more into detail in the second part on that matter. So, most important key point to remember on the endpoint method is measure it always in the stable period. If it's set, it's 40 minutes, you can measure within the 40 minutes, but don't go after and don't do it before, otherwise you will get incorrect results. Okay, let's move to the second reaction. The second reaction is a two-point reaction. It's also called a fixed time, and you see directly from the profile that this is completely different. Well, we'll go through this reaction profile together. So the first thing that we do is to determine the reagent blank. One of the examples that we have for a two-point reaction is a creatinine. As you can see, this is fully yellow, and that will be the reagent blank. Then what we see is we never reach a stable period here. It is never coming to one straight line of absorbance. So we always keep on increasing. Therefore, we need to approach it in a different way. First of all, you see that we have a first incubation period, and this is non-linear. So that means that in that time frame, we are not able to measure anything. You won't have any consistency into your results. However, after a certain time, we see that a linear curve is setting up. That is the green part. And in that time frame, actually, we are able to measure. So what we'll do is we will take a first measurement at the beginning of the linearity period and also one at the end of the linearity period. And if we subtract these two, we always know that we'll have a correct absorbance. After this linearity period, actually, well, the curve will go will still increase, but drop slightly, and there's we will never read any measurements after this linear period. So in terms of absorbance, actually what we can say is that we do not have one absorbance like the endpoint method, but we have two absorbances, one in the beginning of the linearity method and one at the end of the linearity method. And that we are going to, again, multiply by a factor, which gives you the concentration. Examples of this can be creatinine, but also urea. Right?
Yes.
Yeah, urea. All right, how do you know whether you are doing a two-point reaction? Again, by the IFU or by the application sheets. IFU says, mix and start the stopwatch. Then it says, read the first absorbance after a certain amount of seconds, and then you need to read the second absorbance after a certain amount of seconds. So that actually means the first absorbance will be at the beginning of the linearity method. The second one will be at the end of the linearity curve. If we look at application sheet, then we will see that it is prepare and mix and measure. And here it is written one sample at the time. So we are not preparing all of the samples at once. We do one sample at a time. We're going to aspirate it immediately in the instrument, and then we'll wait with the preparation of the next sample until this one is finished. Otherwise, you start the incubation period again, and then you will not be in the right frame. If we look at creatinine, you read the first absorbance after 30 seconds, and you read the second absorbance after 90 seconds. In terms of application sheets, you will see that it's clearly written one sample at a time, and you need to aspirate it immediately into the instrument. That means that the programming of the instrument is set this way that it will wait itself 30 seconds in the instrument and then starts reading and then stop the measurement after 90 seconds. So it's pre-programmed. When we do it on a semi-automate, first of all, we will prepare one sample at a time. Then we're going to incubate, and there's a second difference, inside the flow cell, so inside the analyzer. We're going to add the reagent and aspirate it immediately. You see here that I didn't put any temperatures because of the fact that the instrument is set at a certain temperature. So the CYANVision is set at 37 degrees, so the incubation will be at 37 degrees. Once we go to the green area, we are in the measuring part. So that means that we'll take an absorbance at time 1 and an absorbance at the time 2 after 90 seconds, and this will be subtracted. We know that you need to wait for the preparation of the next sample until this one is fully measured and the result is given by the analyzer. All right, let's give a short demo. I'll change the screens.
So here I start by pipetting the sample. We use as an example today the creatinine, where we need to prepare a working reagent first, but this I've already prepared in advance. So now we can just add it. So for the 2-point reaction, we can only do one sample at a time. So we vortex, and then we have to aspirate immediately for this type of reaction. And that's it.
So what we see as a key point to take home for the 2-point method is that it is easy. You prepare and you aspirate. And it is, well, there's a slight error. It's for creatinine, but it's also for urea. And actually the reading time in the analyzer is approximately 90 seconds per sample. Then, important, you have the incubation inside the flow cell at 37 degrees. So at that time, and for these kind of methods, you do not need an incubator. And then the calculation, as said, we are going to measure 2 points, one in the beginning of the linearity period, one at the end. So that means that it's a difference of two absorbances times the factor, and that will give you the concentration. Good news, this is fully done by the analyzer. You do not need to take that into account. We also call it a fixed time method. We also call it a false kinetic method. And the reason for it, I will revert to that afterwards. What is important? You wait to prepare the next sample here. All right, good. I do also want to give you a little note on the 2-point method because of the fact that the temperature will influence the reaction speed, as it did for the endpoint. However, in this case, as there is no endpoint being reached, it also means that the difference in temperature will give you a different absorbance. So if I do the same reaction at 30 degrees, I will get the red arrow. And you see that at time 2, the absorbance will be lower. If I do it at 37 degrees, then actually you'll see that my reaction time is there. But if I even have a wrongly calibrated instrument, and it would be, for instance, at 40 degrees, then you see that my absorbance, my second absorbance is even higher. So the temperature will influence the reaction speed. Important to know is that if you're working on a semi-automatic way, then you need to make sure that the temperature of the analyzer is well calibrated, that you are measuring at 37 degrees. Secondly, if you do it in a manual measurement just on a photospectrometer, then it is important that the different operators, they work at the same temperature. Well, suppose that you calibrate at 37 degrees and that someone else does an incubation at 30 degrees. At that moment, actually, well, the calibration will not correspond anymore to the sampling measurement, and you will have wrong results. So make sure that everyone in the laboratory, when working manually, works in the same way. All right. That brings me to the third method. The third method is the kinetic reaction. I have two curves here because the reaction can go down, but also can go up. So when we go through the reaction profile, then I always start the same way. We have the reagent blank. And then actually what you see is that the reaction is quite fluctuating. You never see a stable period over time. That is just the way a kinetic reaction works. So we have never a linear, we don't have a linear reaction. We always are in a non-linear curve. How can we sort that out? Because if we are not able to measure in a stable way, we'll never get a right absorbance. So to solve this, what we are going to do is we are going to measure in different point of time and then have different absorbances. And if we just have small time intervals, actually, then we can actually filter out the differences in fluctuation in the curve. So actually, after the absorbance goes too low, there is a time that you cannot measure anymore. So what we will see is we're going to have several absorbances and several time intervals, and actually we're going to just see what is the average absorbance difference over the average time, and that is multiplied by a factor. The examples of these methods are a GUT, a GPT, CKNEC, and so on. All right, how do you know? Well, on the IFU, it's always written, mix and wait for a certain amount of minutes, and then you're going to read the initial absorbance, you're going to start a stopwatch, and then read every minute for a certain amount of minutes. So you need to measure different time intervals. On the application sheets, again, it's written, prepare and mix, and certainly measure one sample at the time. So you need to aspirate it immediately into the instrument, and you need to wait until this sample is finished before going to the next. For instance, on the IFU of GUT, it's written, wait for 1 minute, and then read the absorbance every minute for 3 minutes. In the application sheet, you will find it is one sample at a time. And actually, if you go back to what we told on the 2-point measurement, it's approximately the same. You are having the same kind of procedure followed. It's one sample at a time and an immediate aspiration after you have added the reagent. Okay, so to do this on the semi-automate, what we're going to do is prepare one sample at a time. The incubation time is inside the analyzer, so you add and you aspirate immediately. And then you are going to measure inside the analyzer. So the analyzer will take different type of analyzing intervals in time, and that will give different absorbance, and the calculations are automatically done by the analyzer. Know that you need to wait to prepare the next sample before this one is measured and the concentration is given. Well, I'll switch my screen. So
also for this type of reaction, we start with pipetting the sample. And we add the working reagent that we prepared in advance. And exactly the same as for the 2-point reaction. So also for the kinetic reaction, you need to vortex and you need to aspirate the reaction immediately.
So key points for the kinetic reactions are: it's easy, you prepare and aspirate it directly. You have a reading time in the analyzer, and it's an average 150 seconds per sample, and it is we have 26% of the methods that are this way. It's not, just for the record, it's not Cypress that determines which method it's being used. It is actually related to the biochemical reaction that is behind the coloration, and for many methods it cannot be changed. So then incubation inside the analyzer at 37 degrees, and so no incubator node needed. And then, of course, the calculation is we take different absorbances over different time intervals. Of course, this is done automatically by the analyzer. The most important thing is wait to prepare the next sample. Okay. I do want to give you some notes. First of all, also here we see a temperature influence. You see on the left of your slide, you also see that there are 3 red arrows. So if you would do it at 37 degrees, 30 degrees, or 40 degrees, actually the reaction time will be different. So you need to make sure that the analyzer is well calibrated. And if you do it in a manual way, just on a spectrophotometer, it is important that every operator has incubated the sample at the same temperature. Then also what we see is we can have positive factors and negative factors. This is because sometimes the absorbance goes fully down, and in some of the reactions, the absorbance can go up. So this will determine the negativity or the positivity of the factor. All right. On the next slide, you will find an overview, and I invite you, when re-looking at these slides after the training, we will send you an email within 2 hours after the training with the PowerPoint of this presentation. I invite you to look at it, because here you clearly see what are the differences. Endpoint methods, stable zone, stable period to measure, and you do the incubation outside the analyzer. 2-point methods. You prepare it sample by sample, and then you measure. So, well, you do the incubation in the flow cell. Kinetic measurement, you do the incubation in the flow cell, and you wait until this one is done before you start the other one. All right. So we have talked about the right timing to measure the sample, but there are other attention points to pay to look at when to have a correct absorbance. First of all, respect the intended use. That means that you always respect the sample type. If in the intended use it is given that the sample is serum, well, do not use it with plasma. If it's given serum and plasma, well, then do not use it with urine. So if the sample type is tested, it will be indicated into the IFU. Then the expiry date, don't use reagents that are already expired, and make sure that the storage is well respected. Then, of course, within the application sheet and within the IFU, you will find sample and reagent volumes. Don't mix with the ratios, but also don't mix the full reagent or the full reaction type volume. That means we see that some of the people just lower the amount to have less reagent use. However, this will create air bubbles into the analyzer. This makes false results, and this also makes repetition of results, which in the end leads to, again, more repetitions and more loss of reagents. So please respect it. Okay, that brings me to the second part of this presentation, and then we talk about calibration and quality control. Good. Just a small recapitulation. We had the first step in which we went from the light source to the analog or the digital signal, an absorbance. Then now we need to go from the absorbance to the concentration, and that we do by a calibrator that will be determining a factor. So let's see how this works. First of all, what is a factor? First of all, a factor, it transforms the absorbance in concentration of the analyte. So that means that we can say that the absorbance multiplied by the factor will give you the concentration. And that factor is determined in the calibration process. Also, it means an incorrect factor means always an incorrect result. Okay, let's see what is needed. I do want to have to do a little mathematics with you. So if we know that the concentration of a sample equals the absorbance of the samples times the factor, then we can actually use the same formula for a calibrator. We can say the concentration of the calibrator is equal to the absorbance of the calibrator times that factor. And so what we also can say is if we turn a bit around the formula, that we can say that factor is equal to the concentration of the calibrator divided by the absorbance. That gives you two unknowns for the factor. The one in green, concentration of the calibrator, and the one in blue, the absorbance of the calibrator. Well, I have good news for you. First of all, the green part, the concentration of the calibrator, it is given to you. We provide it to you in the human calibrator. Every human calibrator has a specific table, lot specific table, or on the label, the value of the analyte. So you have a known concentration. And this known concentration is also analyzer specific. So that means that one of the unknown is not there anymore. You have this information. Secondly, when we look at the absorbance, then actually we need to measure the absorbance of the calibrator. How do we measure it? So absorbance, that is what we already did in the first part. It's actually just make sure what type of methodology you have, and then you just measure the absorbance. So let me show you what happens when you have a wrong calibration. First of all, we had the factory of Michelangelo, and who made a perfect David. We discussed that in the beginning of the these sessions. However, so they use a reference which is 1 meter. Suppose that we have 3 laboratories. We have laboratory 1. Laboratory 1 uses the same reference and also is able to produce the same David. However, the second laboratory, they use the same meter, but it is old, and it's impossible actually to see the differences on the bar. So that means that they will produce a David, but it will be slightly different in ratio and in size. And then if you have a third laboratory who uses it, but actually it broke down and we have a shorter meter, let me say it like that, actually, well, they will have the same David, however, they have a smaller David. So it is clear that first laboratory will give you good results. The second and the third laboratory will give you bad results. And that is what we want to avoid. I will give you more information on the point when to calibrate, and then I will also give you more information on how to check whether that meter that you used is correct or not correct. So when do we need to calibrate? There are two type of cases. First of all, you have never calibrated in the past. So that means there is a new analyzer in the laboratory. So you do it after the installation. You do it for every new method and for each method separately. It's not because the creatinine has been calibrated that the albumin has been calibrated. You need to do it for each method separately. Then, if you have already calibrated in the past on that instrument, what will you do? Okay, we're going to check whether the calibration is still okay. And we do that by a quality control. If that quality control is out of range, you need to recalibrate. If that quality control is in range, the calibration is still okay. Other types can be if we use a new reagent lot, if we use a new working solution, and also after the maintenance of the analyzer. In terms of accuracy, we have 3 different levels in terms of standards and calibrators. First of all, the highest level is the calibrator. So that means that it's a serum-based solution or lyophilized solution that you need to sort. We have the multi-calibrator with multiple parameters into it, but we also have dedicated calibrators on CKNEC, CKMB, HPH1C, HCl, and some electrolytes. One level down in accuracy means it's the standard. Many kits from Cypress have an internal standard. Know that you can only use this one for manual and for semi-automatic measurements. What is the reason for it? The standard is an aqueous solution. It's not a serum solution. And so there will be a difference in the viscosity between the sample that you're going to measure from your patient and the standard. That also means if we go to very small volumes, then the differences or deviation can be big. And if we have a difference in volume of the sample, well, then you also have a wrong factor. So with semi-automate, the volume is high enough to do it with aqueous standards. If we go to an automate, we need to do it with a calibrator because there actually the volumes are reduced. And actually also the sample volume is too much reduced to do it with an aqueous standard. And then some of the kits also give a factor on the IFU. When can you use this? Actually, for these type of kits, for GOT on GPT, for instance, the factor is always approximately the same. It is written on the IFU, it's approximately 1,750, but it can be slightly higher and can be slightly lower due to the fact that you have different lot, that you have a different calibration of your pipettes and so on. I would advise use the factor, but check it with a quality control. If the quality control is in range, you can use a factor. If the quality control is not in range, then you're going to need a calibrator to determine your own factor in the laboratory. All right, good. That is the calibration. What does a calibration do? The calibration just says, okay, well, I have a concentration and I'm going to determine just a factor. That's it. But you don't know whether this factor is right or wrong. So we use a quality control to check if that factor is correct. And actually, in the same time, by doing that, you're also checking whether the manipulations you did are correct, that the pipetting is correct, that your analyzer is correct, and that your reagent is not deteriorated. So actually, you're checking a lot of things, and that is actually to see is the factor correct or not. All right. So checking the quality control will always result in clear, correct, and consistent results, and will also improve the professional patient care and improve the credibility of the laboratory and the reputation of the laboratory. This will lead to an incremental growth of the laboratory. All right, good. Let me indicate what the quality control does. So we had the 3 laboratories, from one who using a right reference and 2 actually using a wrong reference. If we use a quality control and we put it next to it, then you will see that for the first lab, the 2 Davids are exactly the same. Perfect, go on, it's a good result. However, for the second lab, if you compare it one to the other, it's clear it's not working. If we do it for the third one, you see as well, the one is a lot smaller than the other one, so we cannot accept it. And there you say it will lead to bad results. So that is what you do. A quality control checks whether your factor is right or wrong. So when to perform a quality control? We recommend to do it every day. But we cannot give you the requirements. It means that every lab is different and everyone has its own policy. The only thing that we can require is that if you have never calibrated in the past, you need first to calibrate and then check the quality control. That is the same after the installation of the analyzer for every new method and for each method separately. If you have already calibrated in the past, first thing, check the quality control. If the quality control is right, you do not need to do anything anymore. If the quality control is wrong, then you go to a calibration and a new quality control. All right. You also see, and we often talk about the Levy-Jennings plots. You see a picture on the sides there for Levy-Jennings, and you see that the days are counted at the bottom on the x-axis. You see that till day 15, everything goes pretty well, and then we have an increase of the values, and at a certain level, even the values are outside the red zones or outside the red lines. At that moment, the quality control is not okay anymore. So what we need to say there is, okay, at that moment, we need to do a calibration again and check the quality control. So, shortly said, calibrations, you do not need to do them every day. You only do it if you do not have a factor yet, or in case you use new working reagents or a new lot. The quality control, the checking of that factor, that you do on daily basis to make sure that all of the results within that day will be correct and that your patients will be treated the right way. All right. What do we offer? First of all, we offer multiple parameter controls. So we have the normal and the biological, the normal and the pathological biochemistry control. This is validated on our instrument and has specific values for the different analytes and also sometimes for the different instruments. Then we have dedicated controls, for instance, for electrolytes and so on. And then we also, to make life easier, we have the biochemistry quality control sets in which you will find one calibrator, one normal control, and one pathological control. Okay. Important to know is what will you do when your quality control is out of range? Suppose you enter the lab in the morning, you do the quality control, and you notice, something is not right. First of all, find the reason, find the cause. Check whether the pipetting was right. Check the storage. Check whether the reagent was not deteriorated or contaminated. Check if the analyzer was cleaned correctly the night before. Check whether the reagent is deteriorated. And also check whether the calibration has given you the right factor. Sometimes it's not that easy to find the root cause behind it, and therefore we can help you. We have created tools, an assistant online. It's a survey that you can fill out And it's there for the CYANVision and for the CYANElite. So what you just need to do is you answer the question step by step, and actually at the end of the survey, you will get information on the possible root cause. So it will guide you through finding what is wrong and sorting it out. Once you have sorted out what went wrong, you're always going to recalibrate, so using the calibrator and determining a factor, and then you're going to remeasure the quality control to verify if it's okay. If it's okay, you can go ahead. If not okay, keep on looking. To help you and to help the laboratories to make a right decision concerning quality control, we also have a quality poster that can be downloaded from the website. You will find the link as well into the PowerPoint that will be sent to you. This is a poster indicating good laboratory practices in terms of calibrations and in terms of quality controls. I will go through it with you briefly, but it's actually just a resume of what we already told today. First thing in the morning, we're going to do an auto zero just to check the optical and the hydraulic circuit of your system. Then we do the reagent blank. That's what we talked about. Then actually, if the calibration was already done, we go to the quality control level 1, the normal quality control. If that is okay, you can go to the pathological one. And then if that is okay, you can go to your samples. Suppose the quality control level 1 is not okay, you find the root cause, you go to the calibration again, and you check again the reagent blank and the quality control. So you turn the loop. In case actually you have never calibrated before, so it's obvious that the order is auto zero, reagent blank, calibration, quality control level 1, quality control level 2. All right. Good. So to remember today is, first of all, to have right absorbances, you need to respect the measuring time. It is essential to reliable results. Secondly, an accurate factor determination is needed and needs to be done in a consistent way. So it also gives consistent and reliable outcomes. Then you need to check that calibration. You need to check the factor by a quality control. That is what you do on a daily basis. Then afterwards as well, Cypress, we offer the tools, the products, and as well guidances on good laboratory practices to always work in this consistent way and to always produce clear, accurate, and reliable results. And so we also can say that laboratories that commit to that GLP approach, that they constantly deliver reliable results, but they also build strong reputations, and they will have a sustainable growth over time.